Welcome to Pre-Calculus. Today we will investigate graphing rational functions with slant or oblique asymptotes, focusing on writing the equation of the oblique asymptote using polynomial long division. We'll take a look at one example. Our function here is f of x equals x squared minus x minus 6 over 4x minus 8. And as with any rational function, what I want to decide first is whether or not there's any removable discontinuities. And we do that before we even look at vertical or horizontal or slant asymptotes, because it can give us a simplified version of the function. So we should remember, how do I identify any removable discontinuities? And the way we do that is by factoring any polynomial in the numerator or in the denominator. So I'm looking for removable discontinuities, and we're going to factor what we can and look for any cancellations. So in my function here, I'm going to start in the numerator. I've got the quadratic x squared minus x minus 6. And so as I set up my two linear binomial factors, I see that I've got to have x and x in my first positions. Those will give us x squared. And then I need to decide what numbers will do two things simultaneously. They'll multiply to that c term -6 and add up to the b term. I don't see a number there, so I'm going to supply a 1, add up to -1. And it turns out that that could be for us -3 and +2. So definitely -3 times +2 is -6, and -3 plus +2 is -1. So that fulfills my two requirements. I'm going to fill those in. So we've factored that numerator. The denominator doesn't have a whole lot to factor. I do notice that it has a common number factor of 4x minus 8. So if I divide a 4 out, I'm left with x minus 8 divided by 4 is 2. Now, what I see in this function is that there is no identical factor above and below. The closest we would get is x plus 2 above, x minus 2 below, but those aren't identical. So even though they're similar, they wouldn't cancel because of the sign difference. So what I would say here is that there are no removable discontinuities. Well, it's good to investigate to look for those. Once you've decided really one way or the other whether your function has removable discontinuities or not, the second thing we want to look for is the equation of the horizontal or the slant asymptote. So at that point, what we're looking for is a comparison between the high power on x in the numerator compared to the denominator. So looking back at the original function, since we didn't have any cancellations, I'm not going to work with the factored form. I'm just going to go back to the original. And what I'm looking for in the original is what's the highest power on x, both in the numerator and in the denominator. And again, what we're looking for, just to kind of announce our task here, is we want to find either horizontal or slant asymptotes. That's kind of our second go-to task when we're graphing rational functions. So as I look here at the high powers, my highest power in the numerator is going to be the square, the 2, power of 2. And when I then look at the denominator, there's only one occurrence of x. It doesn't have a power listed, so I'll supply the power of 1. And when I compare those high powers, I see that the higher of the two is in the numerator. So if that's the case, I do not have a horizontal asymptote. I've got a slant asymptote because the higher power is above. Remember, if the higher power had been below, I would have had a horizontal asymptote. If the high powers were equal, I also would have had a horizontal asymptote. So it's only this one case where the higher power is above. So then once we've identified that, hey, here's a slant asymptote, I want to find the equation for it. Now the way that we find the equation for any slant asymptote is by performing division. Now you can use polynomial long division or you could use synthetic division. What I'd like to use here is polynomial long division. So I'm going to set that up. You put your numerator underneath the division house here. So I'm going to put x squared minus x minus 6 there in the dividend, and then the divisor is going to be my denominator. So I'm going to put 4x minus 8 over there on the left. And with polynomial division, what's very important is to know what to focus on, because there's a lot of terms here in my two polynomials. But basically, I'm really starting with just the first terms of each. And like we do with number division, I want to start off by just dividing those two pieces. So really my first division is going to be x squared from the dividend, first term there, divided by 4x, the first term in my divisor. So that's going to reduce to 1/4 x. And that's what I'm going to report here as the first part of my quotient. It's going to be 1/4 x. Now I want to get the constant as well. So notice we've started to write an mx plus b, and that's what you want with the slant asymptote equation. It should be aligned with some kind of slope other than 0. So I'm going to multiply back 1/4 x times each of the terms here in my divisor. So let's make that multiplication. And what we're looking for is for our first multiplication of 1/4 x times 4x to be the same as this first term in the dividend. And that looks pretty promising. 1/4 x times 4x is x squared. The quarter and the 4 cancel out. And that's the same. So that's good news. That's going to cancel when I do the subtraction in a moment. I do want to distribute to the minus 8 as well. Negative 1/4 x times minus 8 is going to be minus 2x. So at that point, I'm ready to subtract, just like we do with number division. One thing I do to make this step kind of error-free is I want to distribute this negative sign to each term in that x squared minus 2x. And one way you can do that is just call this plus and then switch the terms on the two interior ones. So now that's x squared minus x, that goes to 0. That's kind of what I'm looking for. In fact, I won't write 0 because I want to focus on what's next. Negative x plus 2x is going to be 1x, or just x. And then I want to carry down my minus 6. Once I've gone full cycle, I then turn my attention to the next division. So again, it's important to know what to focus on. So I'm going to circle the first term in my new line there, which is just x, and then I want to again divide that by the first term in my divisor, 4x. And turns out that would reduce to 1/4. I'm going to add that to my quotient, and I'll multiply back. We'll do the subtraction, but at that point we may be able to just stop, because at that point I'm seeing a clear mx plus b equation. But we'll multiply back. So 1/4 times 4x, again the quarter and the 4 cancel, so it's just x. And then 1/4 times negative 8, again minus 2. I'll subtract that. Again, distribute that negative, so make that positive, switch the signs on the inside, and that gives me a remainder of negative 4. Now I could write this out as remainder plus negative 4 divided by 4x minus 8. But what's important for me really is this linear equation here. And that's actually my equation for the slant asymptote. I'm just going to go ahead and put a y equals. And that is ready to go. In fact, I can graph that right now to get ready to graph this equation. So remember, to graph an mx plus b, we start with the y-intercept. That's 1/4. So I do have to estimate here on the graph. So I'll estimate 1/4. And then I'm going to use my slope to graph a second point. So the slope is 1/4. So I'll rise 1. Notice I'm going from quarter to quarter since I'm not starting at an integer. And then I'm going to head to the right 4. So 1, 2, 3, 4. I could repeat that just to get several points, and I'm going to dash that in. That's my slant or oblique asymptote. And then we can reverse that as well. Now, once I get that slant asymptote sketched in, what I need to decide next is, are there any vertical asymptotes? So again, this is kind of the traditional approach to finding the graph of a rational function. You look for removable discontinuities, then you look for horizontal or slant asymptotes, and then you give your attention to finding any vertical asymptotes. So let's remember how to find the VA, or vertical asymptotes. For the vertical asymptote, we're going to look to the denominator. And really what we're going to do is we're going to set that equal to 0. The idea with setting it equal to 0 is we're saying, when is that denominator going to give the function an undefined output? Anytime we have 0 as a divisor, it's undefined. We're not able to do that algebraically. So I'm going to pick up 4x minus 8, set it equal to 0, and solve. So the solution's two-step here. I'm going to add the 8 to cancel the minus 8. And then once I do that, I get the intermediate form 4x equals 8. And then to get rid of that coefficient 4, I'm going to divide both sides by 4. And I have a vertical asymptote equation of x equals 2. And I want to incorporate that here along with my slant asymptote. So at positive 2, I'm going to sketch in a vertical asymptote. So the framework's in place. I have a clear view about where my discontinuity is. It's at positive 2. And then I also have a slant asymptote y equals 1/4 x plus 4. All that's left is to place the actual function. And we do that by creating a table of values. We've got to respond to where our vertical asymptote is to choose our domain. So if my vertical asymptote is at 2, that's really where I want to center my domain. So I'll put 2. I'm expecting that that's probably an output that's undefined. So we'll be on the lookout for that. And then I'll back up to 1 and 0, and then head forward to 3 and 4. So since my function is not super complicated, but involves 2 polynomials, I'm going to take that over to the graphing calculator to get these values. So let's head over to Desmos. I'm going to write the function down, and we'll let Desmos help us calculate our outputs. Again, we're looking for that undefined term at 2. So let's see if we see what we expect. So we'll type the function in, f of x. Since it's rational, I'll create the fraction by hitting divide. In the numerator, x squared minus x minus 6. Down in the denominator, 4x minus 8. So you can see that we've got a pretty good start on our graph. I could include my 2 asymptotes. So the one for the slant asymptotes, y equals 1/4 x plus 1/4. You can see that fits in the graph well, so it confirms that our polynomial long division gave us a good slant asymptote equation. We also had the line x equals 2 as our vertical asymptote. So again, that fits in the function that Desmos is showing. So again, our real purpose here is to get a table. So I'm going to find the table. And I can see that definitely at positive 2, the value is undefined. So I don't really need all these values, -1, -2, but I do need values for 3 and 4. So I'm going to copy down that table. And once I've got that copied down, I'm good to go. That's what I need from Desmos. So we'll head back to our notes screen to finalize our table, our graph. So we made some good choices here, I think, for the domain. We'll fill in for our range. So at 0, it had the value of 3/4, 0.75. At 1, it had the value of 1.5. 2 was, as we expected, undefined. That's my vertical asymptote. At 3, I had the value of 0, and at 4, I had the value of 0.75. So we're ready to graph these points and sketch in our rational function. So at 0, it's going to be above that slant asymptote at 0.75. And then at 1, still above at 1.5. So that gives me information that says this left-hand piece of the rational function is above the slant asymptote to the left of the vertical asymptote. We'll also graph the right-hand piece of the rational function. So that had the x-intercept 3, 0, and then 4.75. So certainly that left piece is to the right. I'm sorry, the right piece is to the right of the vertical asymptote, and it's underneath the slant asymptote. Once I've got that in place, I've completed the task. So just to recap, we determined first whether or not there were any removable discontinuities, which would have been a gap or a hole in the graph. We did that by factoring all of my polynomials in the numerator and denominator. This one didn't have any because there was no cancellation once I found my factors. Once I do that, I want to find my horizontal or slant asymptote, and that's by a comparison of the high power above or below. Here we had a high power above, so we knew we had a slant asymptote, and we found that equation by polynomial long division. Once I found that equation for the slant asymptote, I looked for the vertical asymptote equation, really focusing on the denominator, setting it equal to 0 and solving to get our vertical asymptote equation. Once I had those in place, I found a table, sketched my graph, and it fit well within that framework. So I'm going to let you graph your own rational functions. Thanks for joining. See you soon.